Kakeru Suzuki will present the development of a sensor-embedded smart structure based on snap-through backlink. In recent years, composite materials have been increasingly used in building and mechanical structures. However, the use of composite materials has led to the problem of degradation in the reliability of structures due to extraordinary loads and aging. Structural health monitoring, SHM, is used to quickly detect unusual conditions and confirm the safety of these structures. SHM enables us to check the usage status, detect damage, confirm safety in real time, and reduce the life cycle cost from design to repair. However, the SHM currently in use has some disadvantages, such as the inability to install the sensor externally in narrow areas, weakness against impact, and the need for maintenance of the sensor itself. Therefore, there is a need for a shock-resistant sensor with the sensor embedded into structure. In this study, we developed a sensor-embedded structure that uses snap-through backlink. The proposed structure incorporates a curved beam as shown in the figure, which is subjected to snap-through backlink by applying loads from above and below. The dimensions of the beam are L for the fulcrum distance, H for the curvature height, T for the thickness, and W for the depth to control the backlink load. The structural cell is equipped with electrodes in the center of the beam, and the system is designed to energize when the electrodes come into contact with the backlink. The condition of the structure can be monitored from the presence or absence of the current. This system enables simple condition monitoring and high shock absorption. Prototype NIT cells are used to determine the effect of design parameters on backlink and mechanical properties. This prototype condition for the unit cell are as shown in the slide. We also define the design variable alpha, beta, and gamma in this way using the dimension of the curved beam section H, L, T, and W. By using these design variables, it is possible to back-calculate each side of the curved beam section. Therefore, even if the size of the structural cell changes, cells with the same size ratio can be formed. Compression and cyclic loading tests were conducted on the structural cells. The experimental conditions are shown in the table. From each of the tests, the shock absorption and repeatability of the structure were checked to see if snap-through backlink occurred. This is the load displacement curve obtained from the compression test. The red point on the graph is the backlink critical load, which is the point at which backlink occurs. The two backlink critical load indicates that the upper and lower curved beam of the structural cell buckled under different load. The backlink critical loads are 2.3 Newton and 4.2 Newton respectively, and the backlink occurs when this much external force is applied. This is the result of the cyclic loading test. The figure on the left shows the load displacement curve obtained from the first cycle. From the graph, it can be seen that the structural cell has hysteresis property and shock absorbing property. The figure on the right is the load displacement curve obtained from 3 cycles of the experiment. The fact that there is almost no difference in the graph due to the 3 compression and unloads indicates that the deformation of the structural cell is only elastic. From this, it can be assumed that the structural cell can be used repeatedly as a sensor.